Okay, this is class number 25. It's street routing problems and graphs, and it's part 1. And this goes with sections 5.1 and 5.2 in your textbooks. Okay, so our daily summary. In this lesson, we're going to begin our study of graph theory by taking a look at a special type of routing problem called street routing problems. Routing problems deal with finding the best ways to route the delivery of goods, such as mail, pizza, and packages, or services, such as security or garbage collection or airline flights, to an assortment of destinations. In today's demo, we're going to start off with one question that we need to address, which is the existence question. Is an actual route possible? The answer to this question is yes, and it typically is yes. Then there's a second question to address called the optimization question. Of all the possible routes, which one is the optimal route? And the optimal or best route may depend on one of several variables: cost, distance, or time. Okay, all street routing problems have a pass-through requirement, the requirement that the route must pass at least once through some specified set of connections. This means that each street within a defined area must be covered by the route, and this type of route is called an exhaustive route. Below is a map of the Sunnyside neighborhood, and the same map can be found on page 141 of your text. And so you can see we've got a lot of streets within that town. Got some buildings, a park, we've got a school. And we're going to use this map to consider the various types of street routing problems that we might encounter in this section. One is a security guard problem. We also have a mail carrier problem. We might see a UPS driver problem, among others. All right, so the question is, how might the street routing problem differ in each of these situations? Well, the security guard problem might need to consider walking down all streets, including the ones that go around the park and the school, versus the mail carrier, not all streets. You only need to go down the streets where there are homes or businesses. There's a little bit of a difference there. Mail carrier may also have to consider whether or not going down a street once and delivering to both sides is an option, or if they have to go down the street twice to deliver to both streets. And the UPS driver doesn't have to do all streets either, as their packages, the packages that are delivering probably aren't going to all the homes and businesses in the area. Okay, a map of the city of Königsberg is shown below. It's also on page 143 of your text. The Königsberg Bridges puzzle asks whether it's possible to take a walk around town fully crossing every bridge once and only once, i.e. no bridge could be skipped and no bridge could be crossed twice. The Swiss mathematician Leonhard Euler showed that it was impossible to take a walk around the town crossing each of these 7 bridges only once. So he solved this puzzle by showing that it was actually impossible to do. Right, so notice within this town or city of Königsberg, we've got this waterway passing through it. And then we also have these red bridges. So if we count, here are the 7 bridges of Königsberg that led to this puzzle. Okay, so if you want to press pause, you can take a moment and try these 2 questions out. First one is, can you find a way to take a walk around the town if you're allowed to cross 1 or more of the bridges a second time? And note that you don't have to end up where you start. Another way of saying you don't have to start and stop in the same place. Okay, and question 2 is a little bit different. So how many bridges do you need to travel across a second or even a third time in order to get back to where you started? All right, so again, press pause, try this out. Okay, if you want a challenge, you can go back in and figure out how to do this with a minimum of 1 extra bridge or 1 extra crossing. Okay, and to get back to where you started, you may have already found this, but you would need a minimum of 2 extra crossings. Right, the other thing you may have noticed is that these aren't easy questions to answer. But if you simplify the map given above, you might make it easier to find a solution. So which aspects of the map do you think are important to answering the original question? And which aspects of the map do you think aren't important? Well, let's start with aren't important. You probably weren't too worried about which streets you took to get from one bridge to the other. We also didn't really need to worry about where any of those buildings were or the waterways themselves. It wasn't really important what the bridges were crossing. But the original question, what was important, you had to know where the bridges were. Oops. Let's go back to that page. So the important piece is you had to know where the bridges were and what they connected. So the bridges and land masses were important. And number 6, it turns out that the relationship between the land masses and the bridges are the only things that actually matter when finding a solution to this problem. Taking out all of the excess information leaves us with the graph shown at the bottom right. So if we take a closer look at the process they went through to get to that last picture, notice that when they went from the first picture to the one on the right, they removed all of the buildings. I already simplified the picture that way. Also note that they labeled the right bank, the left bank, and the 2 islands within that. So we want to keep track of those land masses. Right, they then simplified it even further by removing the streets. So this one on the lower left has all the streets taken out. And it didn't matter what streets you used to get from one bridge to the next. So we've removed those. And then in this last one, they've taken out the waterways. But notice what they did hold on to in these last 2 were those banks, those land masses. We've got the right bank and the left bank and those 2 islands. And then over here, again, the waterways are removed. We still have those 4 land masses. And we also have the 7 bridges that connected them. So we've got the 2 bridges that connect the right bank to Island A, 2 bridges that connect, oops, I said that wrong, 2 bridges that connect the left bank to Island A, 2 bridges that connect the right bank to Island A, the bridge that connects the right bank to Island D, and D to the left bank, and then that 1 bridge that connects the 2 islands. Right, so notice here that the lines represent the bridges, and the dots represent the land masses. I also know that you could draw this in a different way, and it would still represent that picture we had above. Let's say we have the right bank, Island A, and the left bank, and Island D. We've got 2 banks, or sorry, 2 bridges that go from R to A, 2 that go from A to L. Got the bridge that goes from A to D. And then that bridge that goes from R to D, you could draw it like this. And it would still represent the same thing as what's above. In fact, the bridge that goes from L to D, you cross that and come around, and we'd still have the same picture. And what's important is what bridges with the land masses, which land masses the bridges connect. All right, so number 7, the key tool we're going to use to tackle the street routing problem is this notion of a graph seen above. So note these graphs will have no relation to the graphs of equations and functions that you may have studied in algebra and calculus. The basic elements of these graphs will be dots, which are going to be called vertices, and lines, which are called edges. And the edges will connect the vertices. And by the way, that's the plural form. Singular is just vertex. All right, so number 8, can you find a solution to the Königsberg Bridges puzzle using this graph if you're allowed to cross one or more of the bridges a second time? And so that's the same question as before, but you might find it easier to do now that we've got that simplified graph. So feel free to press pause and give that a try. Okay, number 9, vocabulary. There's a lot of vocabulary in this section, so we're going to use the graph below to help us with some of these vocabulary terms. And you will encounter a few more terms in today's group activity. Right, so this is not the Königsberg Bridge problem. It's just a new graph. Right, our first vocabulary is right here. We're going to talk about a vertex set. It's a set of vertices in a graph. So note we typically use capital letters to label the vertices in the graph. The vertex set for this graph, if you take a closer look up above, there's one of our vertices, and those are represented by the dots. And if we keep going, we've got A, B, C, D, and E. And then we also want to make note of F, G, and H over here. Right, so that's our vertex set. In part B, we typically describe an edge by the two vertices that the edge connects. So for example, AB is the edge that connects vertex A to vertex B. And edge AB is right here. I note that the edge AB can also be referred to as edge BA because the order that you put the letters in is not important. So the question is, how many edges are in the above graph? Let's go back up and take a look. Got the edge AB we already marked. We've got these two edges here, the third one there, fourth, actually we're up to 5, 6, 7, 8, and 9. There are 9 edges in this graph. Okay, name 2 more edges. I'm going to take a moment and write down all the possibilities while you take a look at the graph and see if you can find 2 more. Okay, I have the names of all 9 edges in there, and note that these 2 edges, there's 2 edges connecting vertex B to C, and you could certainly write them both as BC. That would be fine. Right. Number 3, where's the edge EE? And note this is an example, or this edge is an example of a loop. Since an edge is named by the vertex it starts and stops at, notice that this edge starts and stops at the same vertex. So that's your example of a loop. In the 4th one, we refer to an edge that appears more than once as a multiple edge, or as multiple edges. Which edge appears more than once in the above graph? That's edge BC and CB. So as we noted before, we have 2 edges connecting the same 2 vertices. So that's a multiple edge. In part C, a sequence of distinct edges, each adjacent to the next, is called a path. Keep in mind, distinct means there's no repeats. The number of edges in a path is called the length of the path. So can you find a path from vertex A to vertex D? And what is the length of that path? I'm going to go back up and give you 2 examples. We are going from vertex A to vertex D. So the shortest path is going to have a length of 1, just doing edge AD. Another example, you can make it a little bit longer. You could do A down to B, and over to E, and then down to D. And that would give you a path as well. You're starting at A and ending at vertex D. So again, one example. Edge AD is your path and has a length equal to 1. A second example, we'll name it by the vertices it goes through in the order that it goes through, is ABED, and that has a length equal to 3 because it has 3 edges in that path. All right, can you find a path from vertex A to vertex E? So I'm going to encourage you to press pause, go back up to your graph, try this out, and then press play when you're ready. One example is ADE, which has a length of 2. And another example is ABCBE, which has a length of 4. All right, in part D, a sequence of distinct edges, so again, no repeats here. Each adjacent to the next that starts and ends at the same vertex is called a circuit. So can you find a circuit in the above graph? And if so, what's the length of your circuit? So let me go back up to the top. Let me show you an example of one circuit. Let's use black in this case. We got ABCA. There's a circuit. So notice I'm starting and stopping in the same place. So you may want to press pause, take a moment, see if you can find another circuit in there. Okay, and as this a second example, there's a circuit that goes A to B, E, D, and A, and that has length 4. Okay, number 10, an Euler path is a path that includes all the edges of the graph, and an Euler circuit is a circuit that includes all the edges in the graph as well. So remember, an Euler path is a path, and this has no repeats. So again, it's a sequence of distinct edges. Same thing with the Euler circuit, because the circuits, again, have no repeats. It's just a sequence of distinct edges. Okay, so in other words, we have an Euler path or an Euler circuit when the entire graph can be written as a path or a circuit. So parts A, B, and C go with the three graphs below. So which of the following graphs contains an Euler path, which one contains an Euler circuit, and which one contains neither. So again, press pause, try this out, see if you can identify which is which. And then when you're ready, press play. Okay, and note that there should be a vertex there for C. A dot appears to be missing. All right, so the answers. This one has neither. So this one is the answer to part C. This one in the middle has the circuit. So this is the answer to part B. And this one has a path. So this one goes with part A. And if you're curious, let's see if I can show you a circuit in here. I'm just going to trace this through. So note that I start here. I can get back to where I started. So that makes an Euler circuit. And notice I used all of the edges once and only once. And over here, let's start down here. I come up. Can end up at D. And again, what I've done is used all the edges in the graph once and only once. I didn't repeat anything. All right, number 11. By the way, the graphs that we're studying are not limited to street routing problems. In fact, there's no rule about what the labels of a vertex can be. So what do you think the following graph represents? And this is page 145 in your textbooks. If you take a close look at this, you might realize that it looks a lot like a family tree. And in this case, the vertices, your dots, are the people. So this dot or this vertex represents Philip. And these lines indicate relations. And so Philip's children, Charles and Anne. Okay, on the next page, number 12, how can we use a graph to represent each of the following? What would the vertices represent and what would the edges represent? And these pictures again are in your textbook if you want to take a look at them on page 146. So this first one's an airline route map. And if you take a close look, we've got Tahiti over here. So our vertices or dots are going to be the islands. And these edges or lines that are connecting them are going to represent our flights. So they're going to tell you which islands it's possible to fly between. Down at the bottom of your page, you have one more graph. This is something that Facebook created at one point. I don't know if it still does this or not. What you'll notice is that your vertices or dots in this case represent people. And the edges represent friendships. So if two people are connected by an edge, that means they're friends on Facebook.